Hello, my name is Armando Vieira. I'm senior consultant at Closer, and I will make a short presentation about machine learning algorithms and its applications to big data. This short presentation contains the views of my own and does not represent in any way Closer views. So, what is big data and how it is important to deal with appropriate algorithms to have prominent results? I will start by analyzing the connectionist approach, where we will explain how these machines are able to find features and patterns. Then I will go to applications, and then further on the discussion, I will go also on the deep learnings and also applications of these deep learning networks. So, what is exactly an intelligent machine? Is it Deep Blue intelligent, or Watson, the computer that won the Jeopardy contest, or Google? These machines have reached the level of intelligence of a rat? Well, that are hard questions, and I don't know the answers. However, one thing I know is that machines are becoming more and more capable to solve real-world problems. In this presentation, I will mostly guide you through connectionist approach. What is a connectionist approach? It's essentially machines that learn by experience by correlating similar inputs, similar signals to similar outputs. Let's say when you see the light of a thunder, you expect to hear the noise of a thunder. So you make a relation between these two events. The connectionist approach has a long history, starts in 1943 by backlogging bits, and in 1968 there was an argument by Marvin Minsky against this kind of approach to perceptrons. He claims that the perceptrons are not able to learn complex problems. He was wrong, and in 1985 there was really the first perceptrons capable to solve complex problems, the multi-layered perceptron. So this approach for training machines are completely different from symbolic machines. Symbolic machines are Turing or von Neumann type of machines. They are symbolic, they are serial, they possess one instruction at a time, they can only follow instructions written in the code, and if something is out of place, like a single comma, the program collapses. On the other hand, brains work on a very different level. They are parallel. They compensate the lack of speed of each neuron with a huge parallelism. So when you receive an image, you process the image simultaneously in all the receptors, and is a very efficient structure to make representations of the world. Furthermore, it is very robust. If you destroy some neurons, the brain continues to work perfectly. So the idea behind these connectionist algorithms is to mimic, in some sense, these capabilities of the brain into a workable program or a workable architecture that can be used to solve problems like classification of objects, an image, or a sound, or a time series analysis to predict the future. So these are based on synapses and connections between neurons by these synapses. As a way of a template to our model, we use like the sensory, the visual processing unit of the brain that is well known, that works by layers, and each layer passes features to the above layer up to a point where an object is recognized. So this architecture will be used by creating an artificial neural network that is very similar to this one. And what is an artificial neural network? The simplest concept is that if you look only at a single neuron, you can describe it as a sum of inputs that are passed through weights W1 to Wn, and they are summed, and then they are passed through a threshold or a transfer function that should be nonlinear to create an output. This is very similar to what the brain works with signals, integrate and fire neurons. If you want to go a step further to build a full network of these unities, neurons, here is a simple architecture where we have input layers, the hidden layer, and the output layer. And the signals are passed from the input to the output. You see if the signals in the outputs are similar to the one that we are expecting, and if they are not similar, we backpropagate the signals to the input. The way you do this is called backpropagation error correction algorithm. It is an algorithm that works by minimizing the empirical error. In this way, you adjust the weights, the connections, so that the error at the output layer is minimum. The difference between the target values that we have for a set of inputs and the real values that the network is producing. So this is essentially a mapping device. So you feed the network with some inputs. In this case, a function that is described in the lower left hand, and is sampled by some points in the upper left hand, and then the network in the right upper hand. You see that the network is creating the map using these points, and below is the errors on each point.
So, the neural network is essentially a regression machine that maps inputs to outputs. This is almost for all situations the scenario we are facing with. We can separate problems basically into supervised and unsupervised problems. The most successful up to now has been supervised learning, where you give the machine hundreds of thousands of examples with inputs and corresponding label data of outputs, and then the machine finds what the patterns are, if there are some correlations between these inputs and outputs. The problem is that in some inputs it's very hard to extract features. I mean, for this example, this motorcycle, if you give this motorcycle and train a machine to separate or classify motorcycles from bicycles, it is very hard for the machine because it's only seeing pixels. You have to extract features like the wheel shape, like dimensions, like aspect ratio, like the colors. This is the real hard part for some problems, extract by hand the features. Nevertheless, machines like artificial neural networks can somehow create very detailed representations, maps of problems. In this case, we are applying the concept of classifying simple objects, as you can put it somehow as a child, by just giving some examples to the multi-layer perceptron, and in the end we'll see that the network is able to understand what different elements are and how they relate between each other. So in this case, we give as inputs a series of objects like pine, oak, daisy, robin, and you give some attributes like is or contains, and then you give the respective output for each of the elements. Okay, and here we see the results after training the network, which what we call epochs. It's a number of times we give the set of examples to train to the machine, and you see as we increase the number of epochs, we'll see the more detailed representation of each different object. So in the end, if we do some principal component analysis, we will see clearly that the machine is able to separate the animal from the plant, and even in each of these domains, it can represent the detailed subdomains like rose, daisy, and flower, or tree, oak, and pine. So it separates clearly the different attributes of the elements. This is not memorizing; it's just generalization from a couple of examples. So this is what a multi-layer perceptron can do, it's very similar to what the brain of a child is able to do while learning elements in the world. You see that there are problems like the short problem that linear machines are not able to solve. Nevertheless, these multi-layer perceptrons can solve this problem by separating the input size with non-linear separation barriers. In this case, you see that there are some problems with this approach. Like one of the most important is the curse of dimensionality. You see that if you are training just with two inputs, it's okay. We can fill the space with some points, and then we somehow, in this case, separate the blue, red, and green points and see which one is in each area of the feature space just by counting how many points there are. Nevertheless, if you have not two but 200 dimensions, the size of the search space is so big that you cannot fill all these points. So we have somehow to constrain the learning in order not to overfit the model and try to represent all the features that it has in the input space without learning a model that is more complex than the data itself. And that is very common to occur. So, for instance, in this situation, on the left-hand side, you see a model that is overfitted. So we have a very low training error, but the generalization error, that is when the machine is trained or is looking at points that it never seen before, it gives larger errors. So the model on the right is better than the model on the left. Okay, so this kind of problems is a very common in learning by neural networks. It's called the optimization problem. There is a lot of local minimum. It's very easy to get trapped in a local minimum. These problems does not have unique solutions. They are permutation invariant. So we have to find some way to stop the training process of the machines and to get very clever about the training algorithm. So in the last let's say 20 years, most of the effort was being not so much in creating new architectures for the network, but simply devising training algorithms to avoid getting stuck in this local minimum, like the gradient descendant with stochastic noise that we see here, the convergence toward the minimum. There are lots of algorithms, and it's very important to decide and to choose the right algorithm in order to avoid getting stuck in this local minimum. So how do you train and understand the results from these neural networks? They are incredibly powerful algorithms, but they are also wild beasts, so that you should be treated with care. If you don't treat properly the data we give to machines, very easily we end up with a situation where it's garbage in, garbage out. So concerning the interpretation of the outputs, there is also care to be taken. There are several loss functions. I spoke about the output error, but there are other kinds of loss functions to train the algorithms. Sometimes the outputs are not probabilities, like classification problems. We have to take care of that. Sometimes the algorithm is not the result we are getting is not exactly what we are expecting, and we should transform the outputs or the inputs in order to represent properly the feature space. In this case, for instance, in some cases you have to do some pre-processing, like to reduce the size of the search space by using PCA, principal component analysis, or isomap, or any other kind of dimension degradation technique. Now we'll see some applications of these models to several situations, like Rutherford backscattering analysis, credit risk and the credit scoring, churn prediction, Altel demand prediction using Google Trends, and if you have time, also AdWords optimization. There are just a few of situations where we have been involved, in applying and getting some, in some cases, excellent results with not only neural networks but also other machine learning approaches. The first problem is Rutherford backscattering. Is essentially a problem of trying to characterize the concentration and position of atoms in the surface by bombarding the surface with protons or alpha particles and measuring the energy of the recoil of these particles. So you get spectra of energy for these particles that come out of the surface, and by analyzing these spectra we can extract information about the depth and the concentration of the implantation that is present in the surface. In this case, we have germanium implanted in silicium. Here we see three different spectra for situations where the experimental conditions varied, have been varied, and you see that the problem is very hard because for the same, exactly the same situation, we have very different spectra. So the network has to be trained with this data and have to somehow understand where is the information with signals that look very, very different. So we have experienced different architecture. We will have used a very big neural network where you have inputs, 128 inputs, and then 100 nodes in the first hidden layer, 80, 50, and then the output layer. The errors are quite good, and as you can see here in this graph, the prediction and the real values are in good agreement, except for very small doses. And with this technique, we can save a lot of time in analyzing the spectra. Normally, it takes about one full day for a PhD to analyze the spectra coming from the experiments. And with our automation problem, we are able to do this analysis in almost no time. It's almost instantaneous. So we published these results in the Applied Physics Letters in 2009. We are being the first group in the world to do real-time Rutherford analytics. Here in this problem, Rutherford backscattering analysis. In this case, you see the diffusion of platinum inside the surface at real time. So this is a completely different problem. In this case, we are using contact detail records from a telecom, and from this dataset, we were able to extract information about the social network that is composed by the customers. That is to say, which are the closest friends, which are the persons they call most during the day or during the month. And from this information, we can extract insights from what's happened if one of these elements leave the company, is a churner, and this propagation to his network. From this information, we create a propensity model where you rank all the customers in terms of the probability that they will leave the company. And from this information, we are able to say to the company, okay, let's contact the top most probable most profitable customers in order to avoid them to leave the company. In this other problem, we also applied neural networks to make optimization of AdWords bids. AdWords is a very complex problem because it's a marketplace for publishers and for advertisers, and we have to know what is the right bid to put in order to have the maximum return from our investment in this advertisement. So it's not easy because the market is always changing, and the environment where you try to make predictions is completely different from day to day. So the system has to adapt constantly to the new reality and to make prediction what is the best bid for a given keyword in order to maximize the return on investment. That is to say, you can maximize the conversions or the sales if it is electronic sales on this website. We have been seeing in this plot that we can predict with good accuracy the sales with our model. This is another problem. You have bankruptcy prediction. In this case, we make a scoring model based on the set of data from accounting of French companies. We take about 120,000 companies, and we build a scoring model. And here we see that our scoring model is much better than the scoring models from other authors. The problem that is here is that we have to get information about the health state, let's call it, of a company, if it is in a good situation or not so good situation, from only evidence about bankruptcies. You don't know which is the distance of a company to a bankruptcy. We have to estimate this distance just using black and white examples. We have to somehow create a full gray scale area. Okay. In this plot, we see we have several models A, B, C, and all our models are more stable. That is to say, if we change from 1 year to 1 year, the scoring of the company stays more constant. This is due to the fact that we are using not data from a single year, but from 3 previous years. So our model is more robust. Here we see that by using this model, you can extract information about the health state of the company, that is to say that its proximity to default or to non-default is a function of several variables. In this case, is the EBIT and the current ratio. And you see that this allows us to make the so-called what-if analysis. He also applied these machine learning techniques to fraud detection. Fraud detection is a very complex problem, and we analyzed here with social network tools. It's well known that fraudulent individuals tend to aggregate to other fraudulent individuals. So we use techniques from social networks like the clustering coefficient and the propensity of aggregation to explore whether these networks are formed. Also, we applied to hotel demand prediction by using Google Trends and enhancing the prediction, time series prediction, to see what is the demand of tourists in a given city by looking at the keywords that it's being searched on Google a few months before. In this case, the hotel can know what is the demand for a given month and to adjust prices accordingly. Also for the problem of scoring, in this case was personal credit scoring with credit cards, and here in this plot you see that the data we took before we enter with our algorithms for our customer, you see that the blue and the orange are default and non-default customers, and you see that after algorithm is applied, the results are much better. In this situation, it's very interesting because you have almost 600 different inputs, so it's a very large inputs, and we are entering in the domain of very high dimensionality. And if you ask what is the most important features, in this case you see that there are none. All are important. You see this plot is the importance of features as a function of the number of feature, and you cannot see any winner. So almost all of them are important. So as a conclusion, we may say that artificial neural networks are not a silver bullet. They are very good for many problems as long as you have enough training data available. They are continuous variables and relevant features are known. And you have some guarantee that there is unicity of the mapping. Otherwise, I will not recommend to use neural networks, and lots of care should be taken in order to get the right conclusion. Summing it up, I'll say that neural networks, as a comparison with traditional methods from von Neumann machines, they are inductive, while the machines are deductive. They are distributed, while the other machines are sequential. They somehow create concepts and abstractions by example, and the other they are programmed a priori. So there are quite a lot of difference between the two, and
if you ask, okay, where is intelligence in these artificial neural networks? How they learn from the world? Well, the intelligence and the algorithms that they somehow learn are embedded in the weights. So weights, it's a very messy system. You cannot see what is the rule. You just learn by adjusting the weights. So this is how they learn. It's just, you can call it some kind of a black box. So they are more than black boxes. But if you need understanding the problem and why the results are the ones you are producing, I will not advise you to use artificial neural networks. They will not explain you how they have done the trick. So understanding and interpreting neural networks, please be very careful. Now I will move to a revolution that is called deep learning networks. Deep learning networks have been coming with a fabulous set of results. They have been beating almost all competitions from image recognition, voice recognition, and text analysis. So what are really these neural networks and how they are different from the multi-layer perceptron that we just mentioned? So hidden layer networks, the functional element of a hidden layer network, of a deep layer network, is a restrictive Boltzmann machine. A restrictive Boltzmann machine is nothing more than a probabilistic machine where you have a visible layer and a hidden layer. And the visible layer can be an image with these pixels, continuous variables, but the hidden layer is binary, with age having elements that can be 0 or 1. And the way we train these machines is very complex because these machines are very unstable. Typically, they have a very large number of weights connecting these two layers, and we have to use some technique that is called constructive divergence. That is the way Hinton have devised in 2004 to train these machines, because previously it has not been able to train restrictive Boltzmann machine. They not converge. Here you see the problem. If we present the data at the input layer and then we ask for the hidden layer to create a representation of this input, we'll see that after some iterations, because these machines are not feed forward, they work in both ways. You see that in the end they will converge to some fantasy. So the trick they applied with constructive divergence, they were able to train these networks. And what are the difference between these neural networks and the neural networks that we have just mentioned? The main difference is that they are able to extract features. So in this case, we showed them a 4 million unlabeled image. So this is unsupervised learning. And after training, you have been able to learn about 10,000 features from this data. And what are these features? These features are just characteristics of the data. So you can understand a new data set, a new data point, just by mapping these features. Okay, so by putting different layers on top of this first hidden layer, the age layer, we can extract even higher level features from the data. So this is very powerful as abstract representations of, in this case, image. You see that as we present, as we move upward in the layers, we are creating features at a more abstract level. So this are called generative models, because somehow they not only respond to the inputs, they somehow represent all the possibilities of the inputs. So they can generate the inputs from the data that we have been used for training. So here we see that this is autoencoder, that we present a set of digits and written digits that have been used to train a restrictive Boltzmann machine. And then you put
layers on top of this initial RBM, and after some fine tuning adjustments in the last hidden layer, we can train a multi-layer perceptron just to fine-tune the last elements. Okay, so the supervised learning only occur after unsupervised learning. So we first pre-train the network, we freeze the weights, and only correct the last output, the last hidden layer, in order to correct the prediction of the network. And the results have been astonishing. They have beat almost all the data sets. The records have been beaten by deep learning networks. In this case, for instance, you see that in image recognition, he's been able to separate, to see the guy behind the glasses. So you can separate the image that you present. We separate the image of the guy and the glass. So you notice it is a composition of both images.
As another example, in this case, they apply the deep learning architecture to classify a large corpus of text from Reuters, containing about 1 million documents, and they categorized it in 2 dimensions. And you see here the colors correspond to different topics. And you can see that the machine, in an unsupervised way, can learn particularly well what are the patterns in different text with different content. On the right-hand side, you see latent semantic analysis that is much worse. So what these machines are doing is somehow making an unfolding of high-dimensional data into a low-dimensional surface. So they are discovering patterns that they put together points in similar regions that have some similar meaning. So this is called manifold learning or manifold mapping. As another example, we see here the classification of image and trying to retrieve what are the meaning of this image in terms of text. So you see that the machine are doing a quite amazing job by identifying elements in the particular image, like faces, landscape, mountains, trees, sunsets. It does this by unsupervised learning. So what are the new features of these devices that make them so desirable? One of them is that they are mostly non-supervised machines. They extract and combine subtle features from the data, where they can build abstract, high-level representations of this content. They can handle very high-dimensional data, and they work from inputs to outputs and from outputs to inputs. So they are not feed-forward machines. They are recurrent network machines which have very different characteristics. So somehow these machines can be regarded as dimensionality crashing devices. So they can easily put, let's consider for instance a text that is very high dimensionality data into low dimensionality space with some semantics, some meaning. The applications for these devices are all over, and you can see that they are very good at image classification, video, real-time translation. For instance, one of the recent results was the real-time translation between Chinese and English on the conference. They can also be used for video identification gestures, like detecting when the person picks up the phone in an uncontrolled environment like an airport. So summing it up, we can say that deep learning architectures are able to somehow introduce layers between data and our interpretation of the data, as we call it, the results or outputs. We call these middle layers fixtures. These fixtures will allow us to make a much more detailed representation of knowledge inside these layers. If you want to know more about deep learning, please visit the site deeplearning.net, where you find videos, tutorials, and research papers that have been published recently. There is also a good set of talks from Ethan on Google Talks that you can view on YouTube. And also, I like to recommend a book that is Too Big to Know. Also, a book, Big Data, New Revolution that will transform business, and also Machine Learning in Art.